Hi, welcome to this module, and in this module we will learn analog to digital converters and digital to analog converters. So, when we talk about analog to digital converters, what does it mean and how we can use it. Similarly, if you talk about DACs, short form is ADC, short form is DAC. How we can use ADC and DAC while designing your signal conditioning circuit. So, that is the idea to help you out what kind of ADCs are there, what kind of DACs are there. We will talk about that. There are few parameters that you need to understand when you are designing or using ADC or DAC. So, let us see if you see the first slide, what you get is analog to digital converter. Most signals we want to process are analog in nature, okay, and they are continuous and they can take infinite number of values. For example, if you talk about this particular signal, how many values are in this signal? There are infinite values, right. You can have like this and you go on designing anything like this, there are infinite values, you cannot really calculate. So, and they are also continuous. But if when you talk about digital systems, it requires discrete digital data. So, the analog to digital converter converts your analog information into digital information, right. So, analog and the digital, this is analog signal digital system and this guy is nothing but your ADC. So, examples are microphones, thermocouple, voltmeter, digital meters. So, there are a lot of examples where ADC can be utilized. You can see very clearly that if there is a continuous signal which is right over here, right, and you want to create a discrete signal from this, then there can be a discrete points, right, and if you merge those points, then it is the same information. If you just see here analog input, digital outputs, if you zoom in, this looks linear, right, but when you actually zoom in, what you find is there are a lot of steps in between. Same way digital input and it gives you analog output, it is called DAC. This analog signal versus digital signal for 12-bit digital signal, you can see the plot. Now, when you talk about digital signal processing basics, then digital signal processing converts signals that naturally occur in analog form, such as sound, video, information from sensors to digital form. So, from analog to digital, right. So, analog forms can be sound, video, information and lot of other things which are from the sensors, and it has to convert to a digital form and uses digital techniques to enhance, modify analog signal data for various applications, right. So, a digital system processing system or digital system processing first translates a smoothly varying analog signal into series of discrete levels. You can see here a smoothly varying analog signal into series of discrete values, right. So, this series of discrete values or this series of discrete levels. This series of levels follows the variation of analog signals and resembles a staircase. You can see here it looks like a staircase. Now, to use this, we can use a sample and hold circuit, which we will see at some point in ADC, and this is accomplished by using sample and hold circuits, which is also written over here. An original analog signal which is sine wave and its step approximation is shown. When you talk about signal acquisition system, so what does that mean? So, next the stair step approximation is quantized into binary codes that represent each discrete step. So, when we are talking about converting your analog signal to digital format or digital domain, and you can see this stair step approximation, then you have to further use that stair step approximation and it has to be quantized or quantized into binary codes that represent each discrete step on the stair steps by processor called A to D converter, right. So, there where your ADC comes into picture. So, if you see here there is anti-aliasing filter, sample and hold circuit, and then there is something called ADC. Then there is a digital signal processing, it converts to DAC and then finally reconstruction filter. So, these are the blocks where it starts from anti-aliasing filter to sample and hold, ADC, DSP, DAC and reconstruction filter. So, this is how the signal processing block works, and this is a very basic idea of how the block diagram of DSP system looks like. So, the binary codes are then applied to digital signal processor, which is right over here, right, and which performs various operation on the incoming data, such as removing unwanted interference, increasing the amplitude of some signal frequencies, etc. Once it is processed in DSP, it can be converted back to its, because we finally we require the information that was sent, right. So, after DSP processing the signal, we can be converted back to much improved version of original analog signal by DAC, and the figure shows the block diagram. So, this is a block diagram of signal acquisition system, and here you can see the starting variable is physical variable, followed by a transducer, followed by amplifier, filter, and then there is a n channel analog multiplexer, followed by sample and hold circuit to ADC, and then the channel select and start and stop and sample and hold. The signals are given through the block shown here, which is your system control, right. So, this is how the signal acquisition system block diagram looks like. Now, when you talk about conversion process, then there are 3 steps that you do remember. The first step is sampling, second step is quantification, and third step is coding. These operations are all performed in a same element. So, which is your A to D converter. So, 3 things happens, one is called sampling, one is called quantification, and one is called coding. So, 3 things happens when you convert the signal. Now, what is sampling? Let us see. So, sampling is a process of taking a sufficient number of discrete values at a points on a waveform that will define a waveform. So, suppose I have this waveform, right, like this, and I take sufficient points on this waveform, let us say here, 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 and if I just point it out, it looks like this, no. So, is it sufficient? Yes, it is sufficient, because from just lines like this, like you have seen here, if I draw and if I join all these lines, then you see what happens. You have a similar signal, right. You see this one and this one, that what is called sampling. Sampling is a process of taking sufficient number of discrete values at a point on a waveform that will define a waveform. Sampling converts an analog signal into series of impulses, each representing the amplitude of the signal at a given instant in time. Before a signal can be sampled, it must pass through a low pass filter to eliminate any harmonic frequencies, right. We have to eliminate the harmonic frequency. So, what is the filter that we can use? We can use low pass filter. We have seen the advantage and the diagram of low pass filter, high pass filter, band pass filter, band reject filter in the first lecture, as well as we have also seen in earlier course which was meant for understanding how these circuits can be designed and can be operated. Now, we are using those circuits. Now, after filtering and sampling, the sample level must be held constant until the next sample occurs. So, once you filter and sample, then you have to hold that thing, right, until the next sample. So, this is necessary for ADC to have time to process the sample value. This is done with the help of sample and hold circuit, right. So, this sample and hold operation results in a step waveform that approximates the analog input waveform as shown in this particular figure. Okay. So, this is analog signal, this one, then this is sample version of input signal, and this one is sample and hold approximation of input signal. Okay. This is how your sampling works. Now, further if you see sampling. So, digital system works with discrete states, the signal is only defined as determined times, the sampling times are proportional to the sampling period Ts. Okay. So, if I apply x t, if there is a T s, then I have my value x equals to xs equals xs, which is nothing but t equals to k times T s. So, this is the sampling time or sampling period, this is my xst, this is my analog signal xt. So, when I apply xt and you have a sampling rate or sampling period, then your value would be t equals to k times Ts, right. So, from this plot you can understand what this equation means. Now, once you do the sampling, then let us see the quantification. So, quantization. Quantization is an interpretation of continuous quantity by a finite set of discrete values, means establishing numerical or binary values starting from an analog signal value, right. So, using n bits we may obtain 2 raised to n level, right. Each value of each sample will be have associated n bit binary values, right. So, for n bit we have 2 raised to n levels. So, amplitude quantization approximate its input by discrete amplitude taken from finite set of values. So, if you just want to calculate quantization, then you can use this formula where quantization is nothing but V max minus V in into 2 ratio of V max minus V in and 2 raised to n minus 1. So, if you see here you have a plot here, right, the XQT, XST, and then you have here which is analog voltage or millivolts, and you have time. Now, you have this discrete values here that you have calculated, and if you join these discrete values, then you can form this particular signal, right, or you can break this signal into discrete values. That is another way of looking at it. The point is that for n bits we will have 2 raised to n levels, right, and each sample will have associated n bit binary values. That is very important to remember. Now, if you see quantization error, what does it means? It means the difference between signal value and the associated binary value, right. So, you can very easily see here that what are the errors in this particular block, right. The signal value which is right over here and associated binary value. Associated binary value is, you see there is a difference here, difference here, difference here, and if I plot it, it is like this, correct. So, this is a difference of the signal value and the binary value. This is your error. Now, you can here also see that original analog signal is this guy, okay, and then when you apply to sample and hold, then sample analog signal is this one. When you go for digitized signal looks like this, and if there is a quantization error, then you can see here, right. This is how the quantization error will occur, and then you have, when this is mixed and it is here, then you have this quantization error. So, quantization error should be minimum. Now, effect of quantization. So, what will be the effect? Any one sample in the register signal can have maximum error of. So, that is another thing that you have to remember when you design your ADC, is that quantization error should always be plus minus half of least significant bit, and it cannot be this quantization error can have a maximum value of plus minus half of least significant bit, and the important feature of this error is that it looks like a random noise. So, if you really see, it does not look like some kind of signal, it really looks like a noise signal, right. If you just look at the analog noise, then what you feel like this, right. So, that is another point. The additive noise is uniformly distributed between plus minus half LSB. For example, passing an analog signal through 8 bit digitizer adds an RMS noise of 0.29 by 256. So, for 12 bit digitizer it is 0.29 by 4096, for 16 bit digitizer it will be 0.29 by 65536, right. So, this is very important to again remember that quantization error should be minimum. In most of the cases it is nothing but more like addition of a significant amount or specific amount of noise, and it is uniformly distributed between plus minus half LSB. And if you want to calculate passing an analog signal through 8 bit digitizers, how much RMS noise is added, then we can calculate like 8 is 2 raised to 8, so 2 raised to 8 is 256. If you have 12 bit digitizer is 2 raised to 12 is 4096. If you have 16 bit, 2 to the power 16 will give you 65536. So, 0.29 by 4096, 0.29 by 65536. Then comes another value which is called coding. So, assigning a unique digital word to each sample and matching the digital word to the input signal, right. So, you understand here now that if this is the signal and if I have a higher sampling rate and if I have a higher resolution, what is the difference? That you have to have better sampling rate and better resolution. So, by increasing the sampling rate, that how many times you sample, if this is the TS, if I have a even smaller TS, you see frequency, then I have a sampling rate which is higher, but higher sampling rate will form my analog signal in a better format, right. So, I can reconstruct my signal at some stage in a way better format. Same way goes for the higher resolution. Higher the resolution, you can have a better accuracy of the entire system. Now, if I give an example, then if you have 0 to 10 volt signal, and if you have to separate in set of discrete state which 1.25 volts increment, how did we get 1.25 volts? We will see in the next slide, but let us see here. So, you can write 0 to 7, right, because 0 to 10 volts is there. Let us say output states are 0 to 7, 0.00 1.25, 1.25 to this. So, when you have this kind of discrete voltages, you have output state which is from 0 to 7. Now, the number of states that converter can output is n equals to 2 raised to n. Now, what is our thing? We have said that if we use a 3 bit ADC, then it is 2 raised to 3, which is 8. So, analog quantization size would be V max minus V in by n. What is V max? V max is our 10 volts, right. What is V in? V min is your 0. So, V max minus V min divided by n. So, 10 volts minus 0 volt. What is your n? N is 2 raised to n. So, divide by 8, right. So, we get 1.25. That is why we have discrete states of 1.25 volts each. Okay. So, this is a quantizing. Now, if you talk about encoding, then here we assign digital value to each state for the computer to read. So, if you have 0 to 7, because you have within 0 to 7 you can put your analog signal at an increment of 1.25, that is why you have 0 to 7, and if you want to put 0 to 7 in binary state, then you can easily use it, right, because it is 3 digit we are using 3 digit A to D. So, we have 0 is 000, 1 is 001 and so on. You have 7 equals to 111. You guys know it, right, how to do it. So, 2 raised to 0, 2 raised to 1, 2 raised to 2, that will be your 8 bit. Okay. 3 digit or 2 raised to 8 is 256. So, Nyquist theorem. Now, this is again very important. A band limited analog signal that has been sampled can be perfectly reconstructed from an infinite sequence of samples if the samples rate Fs exceeds 2 Fx samples per second. So, where Fx is the highest frequency of the original signal. So, what it says that for an analog signal that has been sampled, if you want to perfectly reconstruct, then you should have a sampling rate which exceeds 2 times f max, where f max is your highest frequency original signal. So, if the analog signal does not contain frequency larger than 1 by 2 fs, then there will be an aliasing error. We will see what is aliasing error. Okay. So, aliasing is when digital signal appears to have different frequencies than the original analog signal. That is your aliasing. So, where your digital signal appears to have a different frequency. We will see what is aliasing in the next slide. And then there is a Velveno postulate which says that if your f max is largest frequency component of the analog signal, then you must sample more than 10 times f max. Why? In order to reconstruct digital samples to look like the original signals when plotted on a voltage versus time graph. So, if you have your sampling which is 10 times then your f max, then you can reconstruct your digital samples exactly or to look alike your original analog signal. Now, if you see here, you have 2000 hertz signal amplified at 200 hertz signal amplified at 2000 hertz, you can see here. Now, 1000 hertz signal amplified at 2000 hertz, you can see this waveform, and 200 and 2200 hertz amplified to 2000 hertz, you can see this waveform, right. So, here you can see very clearly that there is a aliasing error, because if I do this, right, then you see if I am reconstructing this signal, this is what I am getting, but what is my original signal? My original signal is this. Is not this, right, it is not this. So, this is my aliasing error. That is why we should always have Fs greater than 2 times your f max, right. So, now suppose you talk about here maximum frequency component of a signal Fc is 9 hertz, that is 9 cycles per second, and sampling rate would be Fs equals to 72 samples per second or 8 samples per period. In this case, Fs should be 2 times Fc. So, 72 is greater than 18. Is it correct? No, right. Therefore, but Fs is what 72 samples per second is greater than 2 times Fc. So, 72 is greater than 2 times Fc or not, is greater than 2 times 9, 2 times 9 is 18 hertz, 72 is greater than 18. So, we have stick to the Nyquist rate, and that is why the signal can be completely recovered from the sample except quantization error, which is not shown here. Now, if I do not follow the Nyquist rate and if I violate the Nyquist rate, which is right over here, then the signal cannot be recovered from the samples. You can see very clearly, right. You can see how it is violating, and because of that the signal that I am reconstructing is very different from actual signal, which is right over here, correct. So, if you do not adhere to the Nyquist rate, then you will not get the reconstructed proper signal. In general, both phase and frequency will be altered if not sampled at a sufficient rate, and the aliasing, the change of frequency and phase due to insufficient rate of sampling, is called your aliasing. Now comes to your sample and hold. So, to convert your analog signal to digital ones, we require the sample height until the next sample occurs, right. So, digital one is needed to keep a sample's height until the next sample occurs. Result is a step waveform, which is shown here, right, sample step waveform. This is our original signal, right, this is our original signal, and this is a sampling period t. This is sampling instance which are shown in the plot, and if you see here, what is the need of sample and hold circuit? The need of a sample and hold circuit in most of the ADCs today, they have built in sample and hold circuits. Some early ADCs did not have that, and if the input signal to ADC changes by more than 1 LSB, then during the conversion time of one sample, then the output digital result can have larger error, right, and depending on location of the sample taken. Similarly, most ADC implementation without sample and hold functions are subject to this type of error, and possible exception is the flash converter due to its high conversion rate. So, except flash converter, other ADCs will suffer if you do not use sample and hold circuit. The ADC requires a non-zero amount of time to convert a sample to a digital time or form. Let the time required to digit one sample be represented by Tc, which is right over here, right, and during the process of converting a sample, the input voltage will change by delta V, which is right here, right. So, this is the signal actually, and we are trying to see how we can use the sample and hold. During the conversion process, the ADC without SH will continuously see the input, right. So, the one that is not using as say a signal and sample and hold circuit, we just see the input signal continuously, but if the signal changes to delta V, right, then more than resolution of the ADC, then there will be error, because if you do not use sample and hold, then what you see is this signal which is going here, right, but if our error is more than delta V, right, or the signal changes more than delta V, then it is difficult for ADC to follow, right. So, there will be an error. So, that is the importance of sample and hold circuit. Now, an example of sample and hold circuit is given below, and the role of the capacitor is to be charged quickly during the sampling time and to hold the sample voltage until next sample has to replace it. That is the role of the hold capacitor. So, when you sample it analog signal, then you have to hold the capacitor and you have to resample it. So, input buffer amplifier offers a high input impedance, which is right over here, for a fast charge of the capacitor, and the output buffer, which is right over here, has a high input impedance denying the hold capacitor to discharge. So, having a constant value at the input. That is the role of the two buffers, input and output buffer across the capacitor, and this is how your parameters for ADC will work. So, to understand how the ADC works, you have to go through these parameters, understand how the coding works, how the sampling works, how the quantization effect works, how the sample and hold circuit works, and what is the Nyquist theorem, what is the Nyquist rate, why Fs should be greater than 2 times F max. If you do not adhere to that, what kind of signals are changing. This is what is given right over here, right. So, in the next module, we will see how the digital to analog converter works. All right. Till then, you read this, and I will see you in next module. Take care.